Hello and welcome to my Physics Lab 3 presentation on black hole. The purpose of this experiment was to first create a model that calculated the mass of a black hole via the law of gravity, and then create another model which used the previously calculated mass to find the initial velocity needed for a ship to pass by the black hole safely. Physics principles used in this lab were Newton's second law, which states force is equal to the change momentum per change in time, or F equals ma, and the parallel and perpendicular components of force, which state that net force can be broken up into two components, with parallel force affecting the object's speed and perpendicular force affecting the curve of motion. The equations used in this experiment were Newton's law of gravitation, Newton's second law, and the velocity and position update equations. Here's a preview of my results. And for our models, the part 1 model modeled the orbit of a planet around a black hole, calculated Fnet with parallel and perpendicular components, and then using those components, used iterative prediction with the law of gravitation to calculate the average mass of the black hole. For part 2 of the model, it modeled a ship escaping the event horizon of a black hole using iterative prediction to plot the ship's position in relation to the planet and black hole. Code for part 1, here's my initial seed, which changed the planet's orbit around the black hole. Constants with delta t being 86400 are calculations for velocity initial, and multiplying velocity by the mass of the star to find momentum, delta v and delta p over delta t, which gets us Fnet, and then separating Fnet into perpendicular and parallel components, allowing us to calculate Fnet by just simply rearranging the law of gravitation. For part 2, we used that same mass of the black hole along with other constants to calculate the speed of both the planet and the ship in relation to the black hole, with these equations down here representing the ship speed and the planet speed. Now, in here, it shows the force of the black hole on the planet and the force of the ship on the planet, as well as the force of the black hole on the ship and the force of the planet on the ship. And with these, we can then plot to see how we need to rearrange our initial velocity to make sure the ship passes by safely. Here are our results. For part 1, the black hole mass was plotted to be 7.68 times 10 to the 33 kilograms, and for part 2, the ship initial velocity was negative 4.62 e to the 7 and 2.5 e to the 6, 0 meters per second. And here is an image of the ship's trajectory around the black hole. Discussion. What does it mean? The perpendicular and parallel components of net force are different than that of the change momentum, as net force is an instantaneous value, while change momentum is taken over a span of time. While Fnet can be determined from momentum, change momentum is unable to truly showcase values at an instantaneous point in time. What if, to create a trajectory for the ship to begin an orbit around the black hole, there would need to be a reduction in the x direction magnitude of velocity and an increase in the magnitude of the y direction velocity. These changes would allow for the ship to travel in an upwards trajectory instead of towards the black hole, ultimately creating an orbit akin to that of the planet. These velocities would also need to be faster than the velocity of the planet, allowing for the ship to orbit safely around the black hole. In conclusion, this lab showcased how the law of universal gravitation, net force components, and iterative prediction can be used in tandem to solve for a rough estimate for large-scale values. To add, as this lab was purely computational, there was no system or surroundings for these experiments. Thank you for watching.